Selecting the right path and right method is often crucial in learning mathematics. Just as a traveler needs a map to navigate unfamiliar terrain, you need effective strategies to understand complex concepts. When it comes to differential geometry, choosing the right resource, understanding the correct learning method, knowing what to read and what not to read, planning to tackle the most challenging aspects of the subject comes as the first important factor even before you sit down to solve the problems. In this series of videos, you will get a complete roadmap in understanding how you should learn and tackle the problems of differential geometry, pick up the right books, resources, tackle challenging problems, thereby making your understanding of the subject clear, beautiful, and profound. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to the first episode on a series of further learning on the subject how to learn differential geometry. Before we go ahead and start learning the methods, books and resources, first we need to learn what is differential geometry. So first let us discuss and understand what is differential geometry in the next part of our video. Here is a clear definition as it says that differential geometry is a mathematical discipline that studies the geometry of smooth shapes and smooth spaces, otherwise known as manifolds. Well, manifold being a technical term, we will take that part later. But what is important is that differential geometry itself comprises of two words. The first is differential. Now, when we talk of differential, we mean to say that it uses calculus, both differential and integral. It studies different kinds of shapes and surfaces, and it is local, not global in nature. Now, what do I mean by local, not global in nature? This will come more clear as we move ahead. So from this part, it is quite clear that differential geometry, the first word differential, is that we need to use extensively what is called calculus. The second thing is that it definitely contains geometry, geometrical properties. From non-Euclidean we move into non-Euclidean, and it basically studies the shapes and size of the objects. So taken these two, I would say, words together, differential, meaning the usage of calculus in geometry, we will be primarily using non-Euclidean shapes and objects. That is what geometry comprises of. So both these using calculus in order to understand different type of shapes and size and objects is what comprises of the discipline differential geometry. And here you can see that the essence is basically nothing but the core idea of using differential calculus to analyze and understand the geometrical shapes. So this gives us a literal or a kind of a very easy understanding of what is differential geometry. However, if we dig a little bit more deeper, we see that in the differential word, we are using differentiation because we would be learning infinitesimal differences or differentials, which is a fundamental concept of calculus, and all the rules of the calculus will be applied here. When we talk of geometry, this means that the surfaces, the structure, where all the physics or all the geometry is taking place. Using calculus means that we are not using it for flat space here. We are using curves, shapes, sizes, and some more exotic shapes which we are going to see. And the underlying structure of the whole physics or the mathematics which actually happens on the geometrical surfaces. So from here, what we can see is that differential geometry again is a branch of mathematics which focuses on the study of geometric properties using the rules, primarily the differential calculus. So from here, what we can deduce is that it uses derivatives, local analysis, tangent space, and connections to different type of differential equations. What do we mean by local analysis, tangent space? All these things one by one I will be clearing up in the next part of the video. So in this part of the video till now you have understood why it is called differential geometry, what are the usage of differential calculus and geometry, totally comprising of the subject of differential geometry. Now as you see that the first thing is that differentiation means using calculus. So there can be an obvious question in your mind which is this: why you need to use calculus. I mean to say, why we are not using any other mathematics. We could have used probability, we could have used discrete mathematics, but why we are using calculus, that part will be clear in this part of the video, because until you understand the real need of calculus, differential geometry again won't be very clear to you. So the first thing is that calculus, particularly I would say differential calculus, is crucial for studying geometric properties, like for example the curvature that you can see, the length and area changed on curved surfaces. So we use in case these rules actually applies on manifold, which are, I would say, much more broader or generic definition of a curved surface. We will look into that. But from here what becomes important is that we are using derivatives to finding slopes, and we are using integrals to find areas and volumes to quantify these changes. So both differentiation and integral will be used, and this one will be for finding slopes and this one will be for computing the total, I would say, the changes. Now, calculus also helps us analyze the properties of curves and surfaces such as curvature, torsion and arc length. Differentiation and integration are used to compute geometric quantities. For example, geodesic, as you can see right on the screen, is the shortest path between 2 points on a curved surface. This is required for solving a system of ordinary differential equations, and also they help us to find slopes of tangent planes, directional derivatives, which ultimately leads to curvature. So the different, I would say, aspects, the different calculation on curved surfaces, for example, calculating the torsion, the arc length, the geodesics, the tangent planes, all these are required because these are actually calculated through calculus. So this actually shows you the real usage of calculus. However, I will show you another simple pictorial description which will make things clear. So I have put this on the thumbnail also. Now you can see this one where these lines, I would say geodesics, are particularly converging. It has got a positive curvature. In this kind of a cylinder, you can see these straight lines are not converging, or they are traveling parallelly. So that got a zero curvature. And in this kind of a shape, the geodesics are diverging. So they have got a negative curvature. Now, this is all good on the surface level, I mean to say, showing these diagrams. But what happens when we use calculus is that we take those weird, I would say, curvatures, and this is where we plot. This is a kind of a shape. For example, I am drawing this onto a flat surface, and then what I am doing, I am dividing these into infinitesimal small, these blue boxes. That means what I can say that I am using calculus, or for example, I am using dy by dx in order to get a dA. That means a differential area. So this is what all the lines and the geodesics that you can see on the left hand side on the spheroid and the cylinder, etc., can be further taken into a plain paper, and I can subdivide them and then use the rule of calculus and get the differential area. Why I need the differential area? Otherwise, how would I be able to compute the curvature and the different lines, points, etc.? So that is why we are using the calculus. So that is how this arrow shows that this dA, or the differential area, is actually coming from those oblate spheroid or the cylinders and spheres and everything. So this fairly gives you an idea that why you need to use calculus, and this diagram also shows you further. Now, there is a technical term which I won't go, which is called smoothness. That means smoothness of a function is actually a property which is measured by the number of continuous derivative. That means how much continuously you can find the derivatives in the same domain. So continuous derivative, what do we mean by continuous derivative? Means the function is differentiable and its derivative is a continuous function. So if f is differentiable, f prime x0 is continuous. So this graph, as you can see, this line, it is a differentiable function. This is also a differentiable function, but this is not a differentiable function. As you can see, the line has broken, so it is not continuous. So if I take the same shape and if I try to, make those boxes, these boxes means we are dividing into small, infinitesimal small, shapes. So these are differentiable structure. So there is another mathematical interpretation which is called a differential manifold. I am not coming to that, but you can talk this as a differentiable structure. What is a differentiable structure? That means it has got a continuous derivative. How do you see the continuous derivative? This one, this red line, this one. As you can see, this is continuous. So this part can be called as a continuous derivative. These are differentiable structure, and continuous derivative means what? The function is differentiable and its derivative is a continuous function. Further, you will see that there are various usage of calculus also in differential geometry. So if I want to calculate the curvature of kappa on curve R3, here you can see this one, this r prime t and r prime prime t are the first and the second derivatives with respect to t. So that is how we calculate. Even, for example, if you are calculating a surface parameterized by Ru and Rv, then the partial derivatives are given by this. Even the geodesic equation, as you can see, which describes the shortest path between points on a surface, it is a second order differential equation, and it involves this one, which is basically the Christoffel symbols. So from here we can deduce this, that calculus is not just about differentiating curved surfaces. It is basically the heart, the essential language for the different type of changes, and these changes will happen in differential geometry because we are extending familiar mathematical tool to a fascinating world of curved spaces, which is actually differential geometry. Now this actually proves that the usage of calculus, why we need to use calculus, what are the surface areas, and the pictorial diagrams all gives you and proves you pertinently that the usage of calculus is evident and very important to learn in differential geometry. Now there might be a question that calculus again is a huge subject which you have already learned in your college or undergraduate days. But are there certain areas of calculus which are predominantly very important in differential geometry? So I might ask this question: which topics of calculus are more pertinent to differential geometry? Definitely the entire calculus is very important, but yes, it might happen that you need to focus on certain areas of calculus so that your learning of differential geometry is much better. Similarly, for example, you are learning quantum field theory, you might say that which part of quantum mechanics or mathematics will be important to QFT. So let us look at what are the topics of calculus which are very much pertinent, and this will give you an idea that all those areas you need to emphasize, you need to relearn and learn into a solid fashion. So the first thing would be partial derivatives, and the question is why? The answer is that these are essentials for analyzing geometric properties, because here it won't be a single derivative, there will be multiple shapes and objects and curvature and tangent planes which are changing. So number one is a very good understanding of partial derivatives. The second thing which comes is vector calculus. Again, why it is so? The reason is that vector fields, for example, line integrals, surface integrals, these are again very, very crucial, because these line integrals and surface integrals will be used in calculating the volume or the surface area of different shapes and sizes. So in order to do that, you need vector calculus. The third thing that you need are multiple integrals. Again, the question is why? Because it comes into play when calculating quantities like surface area and volume, where definitely one single or two double integrals won't be possible. You might need multiple integrals to calculate the complex curved shapes and use the integration techniques, etc. So partial derivative, vector calculus, and multiple integrals, these are the pivotal force. These you really need to analyze and learn and get a solid understanding. But however, there is one more important thing which I would like to focus on, which is called vector calculus. Again, the reason is why. You see that in terms of electromagnetic field in physics as well as in geometry also, divergence, gradient, curl, etc. becomes very fundamental in differential geometry. So if you really want to learn, for example, a kind of a flow, a kind of a curl, things are happening, how these shapes are twisting and turning, these bends, the shapes that bends, etc. You really need to have a wonderful understanding of vector calculus. Now this is a book recommendation. although there are many books on vector calculus, H.M. Shea's book on div, grad, curl and all that, an informal text on vector calculus. This is really a very good book which you can quickly go through in order to get a hang over vector calculus. And you see, the book actually is important because before starting the book, the author tells that in this subject, vector calculus is presented in the context of simple electrostatics. So it assumes electrostatics and then it explains. So first, much of vector calculus are invented for use in electromagnetic theory. So as you now can understand that although we will be using in differential geometry, the invention of vector calculus was because necessity is the mother of invention. So the necessity was to define the div, grad and curl of electromagnetic theory. And I have highlighted in case some mathematics is best discussed in a context which is not exclusively mathematical. And I like this context that the best part of mathematics is discussed when it is not exclusively mathematical. So this book would give you a very clear understanding of vector calculus. The next few more important topics of calculus which will be very essential in differential geometry would be differentiation. Definitely you need to learn that. The reason is that it deals with vector fields, operations where differentiation will be required, how functions change, etc. And differential equations, very important. Why? The reason is that it describes the motion, the speed of arc length, etc. And it describes all the complex phenomena in geometry as well as physics. So differentiation using the differential equations are very important. Now there are certain few less important things which are worth mentioning, that Green, Stokes and Gauss's theorem. These are, I mean to say, not absolutely essential, but if you know, that is okay. But in an initial differential geometry, the focus might be on the core concepts, for example, manifold metrics and differential forms, and these can be introduced without explicitly using Green's theorem, Stokes' theorem and Gauss's theorem. So if you want to ignore Green, Stokes and Gauss's theorem, you can, but if you know, there is no harm into it. So this gives you an idea that these are the topics which you can revisit, relearn, or if you're learning calculus right now, understand that these topics will be extremely important and very pivotal, a pivotal force in understanding the course of differential geometry. Now all these are taken fine. Now the question is that what are the best books in terms of calculus that would give you an understanding? So recommended books for calculus, coming into the next part of the video. The first book which I would recommend is this one, which is I would say a kind of an encyclopedic huge book. It contains almost 1,000 pages, but it is good. Thomas Calculus Early Transcendentals. These are not transcendentals. It's a kind of a complete book, but it is very heavy, more than 1,000 pages. It is good because it gives you one single book which you can pick up from your store and you sit with a pen and paper. It will give you everything that you need to know. So here is my few points on this. This is one book which teaches you everything. It covers everything that you need to know. There are a lot of simple illustrations and exercises which you can do. And most importantly, the last, that is the fourth point, it assumes that you know nothing and it starts right from the grassroots level. So one single book which will cover up everything in calculus. If you are an absolute learner, absolute beginner, and you don't know anything about calculus and you are a self-learner, this book would be very good. Sylvanus Thompson and Martin Gardner's Calculus Made Easy. I've cited in numerous of my videos, but still it is worth mentioning. It is very simple. You don't need any teacher or any tutor. You can learn on your own. But remember, there are not much partial differential equations over here. If you're taking the first step towards calculus, yes, and it is the most, I would say, simplest, although in English it is two superlatives degree are coming. It's the wrong English, but I would say the simplest explanation of calculus, it's a must-read book. Now, if you're talking of differential calculus or differential and integral, this book again is a gold. It is a gold mine which you can go on digging and it will unearth all those unearthly great pleasures and I would say revelations. N. Piskunov's Differential and Integral Calculus, very effective, a little bit older version of this book. It is by Mir Publishers, Moscow, and it explains the fundamental concept with lot of rigor. So it's a mathematical book, remember, it's not something that would give you a very easy understanding, and Piskunov's book is the best in terms of mastering single variable calculus, remember, and it covers both differential and integral. So this would be a very good book when you have a little bit hangover calculus. This book would give you everything related to learning the differential integral calculus. If we're talking of the partial differential equation, this is another book, Introduction to Partial Differential Equations by K. Sankara Rao. You can use this for NetGate also, and it is the best book. It is very user friendly. That means I've read the language is very simple, easy, friendly, and it carries a lot of, I would say, proper and simple explanation. The partial differential, another very good book which I came through is this one, which is Yehuda Pinchover and Jacob Rubinstein, Partial Differential Equations Introduction. These are the two authors. I just thought to give their pictures because both of them are great. And this book is very nicely written, and you can go through many exercises, etc. So it's wonderful. And there are a lot of solutions available on the author's web page, and very well explained. And this is the Google Scholar screenshot of Yehuda Pinchover. Is a great mathematician. You can go and understand the details over his Google Scholar page. Okay, so the last book for partial differential equations would be this one. It is by Peter J. Olver's book on Introduction to Partial Differential Equations. More or less it's good. It covers weak solutions, burgers, PDEs. You can go over. I mean to say, if you're a self-learner, then you can go through this book, and you can check out a lot into authors' websites for videos on PDE solution. Okay, now you don't know, maybe not a very familiar book, but it is absolutely, I would say, a gem. And this is by a first code in differential equation with modeling applications, and it is by Dennis Zill. He received a doctorate in applied mathematics from Iowa State University and is a former math professor of mathematics at Loyola Marymount University in Los Angeles, Loras College in Iowa, and California Polytechnic State University. He is also the former chair of the mathematics department at Loyola Marymount University, and he currently holds the title of Professor Emeritus of Mathematics. I just had to tell you a little bit about Professor Zill because he is not a very familiar figure, but this book is, I would say, a cream, a great understanding, very simple. It's a must read for those who are learning calculus. So here you can see the content. I've just given you an overview. It starts with introduction to differentials, first order, then goes into modeling, higher order differential equations, and finally ends with numerical solutions of ordinary differential equations. Again, it's not covering PDEs. So remember that. For PDEs, I have already shown you the book. So if you tell me that what this book is so special about, then here I would like to show you that in this book, Professor Zill has marked this in red. I thought this is very important to learn. That I want to tell you to read this textbook. And you see he put an asterisk sign. Why? Because, but do not read this text like you would a novel. You should not read it fast, and you should not skip anything. Think of it as a workbook. So remember, this is a workbook. By this I mean that mathematics should be read with a pencil and paper at the ready, because most likely you will have to work your way through the examples and the discussion. So never read this book lying on a couch and this is not for reading. It is a workbook, so you have to have a pencil and a paper and ready things with you. Before attempting any of the exercises, work all the examples in a section. The examples are construct to illustrate what I consider the most important aspects of section. And then it writes, I tell my students when reading an example, copy it down on a piece of paper and do not look at the solution of the book. So, as just an instructor, as a professor would do, step by step, he has actually shown that this is a workbook. It should not be read as a novel. You should have with a pencil and a paper. And the exercises should be worked. And you should, when reading the example, copy it and do not look it in the solutions of the book. Perfect instructor of a great mentor. So this is my honest opinion. It has got a very clear explanation, making complex things very easier. It has got no rush, so it has got a very step-by-step approach. It has got modeling applications, real world application and modeling scenarios, which becomes very pertinent and important so that you can get an understanding that differential equations, how practical it becomes. There's a huge amount of variety of examples. And most importantly, these books contain a lot of practice problems at the end of each chapter, and this will help to solidify your understanding and prepare also for your examination. As has been pointed out by Professor Zeal earlier, that you need to solve those problems. Another, I would say, not much celebrated person which comes up in terms of recommending a book is this: Differential Equations with Application and Historic Notes. Now, you see that I am giving you so many textbooks. It doesn't mean that you need to purchase or go through all the books. You can pick up any one, but I really don't know what is your background, what is your interest. So I'm laying out a myriad of different books and their styles and their knowledge, skills, depth, etc., so that you can pick it up. Anyway, so here is George Finlay Simmons. He was born on 3rd of March 1925 in Austin, Texas. He received a BS degree from California Institute of Technology in 1946. He received the MS degree from University of Chicago in 1948. And after finishing his PhD from Yale University in 1957, he joined Colorado College as a lecturer. Now, I will show you definitely, because historical notes are important to get a better understanding. Here is my honest opinion of the book. It covers more material than typically it should be. The first introductory book covers hypergeometric equations, and most chapters, including lengthy appendixes on mathematicians like Newton, Euler, Gauss, and the writing style is very engaging. A quick grasp over the content of the book. This is what it is. As you can see, it starts with the nature of differential equations, etc. Then it goes into first order, second order, power series, Fourier series, partial differential equations, and it completes with calculus of variations, nonlinear equation. So 643 pages, very dense book, thick book, but it is good that you get a very good understanding of differential equations. So now we know that what is differential geometry, what is differentiation, why we need calculus, and in order to learn that calculus, what are the things that you need to know, what are the books, what is the level, and which one you can select it. So this part of the video gives a complete understanding of the differentiation part. Now in the second part of the video, you need to understand the geometry, and the challenge lies there. So the question that you might now have here in your mind is that what kind of geometry you need to understand. We understand that it is not Euclidean, but what kind of geometry that you need to understand. I will give you an understanding of what kind of geometry, so that before you jump into differential geometry, these things will become clear. Now this is a note which you need to understand. Differential geometry actually builds upon certain key areas, but it does not have any specific geometry which you have to go through. There's nothing as such. So the first one is that yes, you need to have an understanding of points, lines, and planes. Now why is that? Because based on these, this will be extended, because points won't be points, lines won't be lines, planes will curve into geometric and tangent planes, etc. So a good understanding of this part will be required. Distance and angles form the Euclidean geometry. This will be required because these distances and angles now will be measured in terms of the metric, the Riemannian metric, etc. So you need to understand that. And the basic shapes, yes, you need to understand the basic shapes and the Euclidean coordinate system. So this is what you need to understand. What I'm trying to make a point is that in Euclidean geometry, these are the basics. We all know that. But remember, these should have a solid foundation. So here is an analogy. Imagine it as a launching pad. So the foundations like shapes, distances, etc. will become building blocks, and they will actually become more and more and more abstract, and things will become more complex. So this understanding will be required. The next thing which actually creates the challenge is this one: spatial reasoning. Now, why I'm talking of spatial reasoning? Because the space that you see in Euclidean geometry, that would be changed to something different. So differential geometry will be dealing with more than the familiar 3D spaces. Things will become totally different. Also, you will see there is an amount of analytical thinking which will be required, because as you see that it heavily depends on calculus, which is a kind of an analytical thinking. Okay, this is pretty important because differential geometry deals with objects that exist in spaces beyond our familiar 3D world. So spatial reasoning allows you to visualize and manipulate these objects mentally. So you can imagine a curved surface not just as a picture, but as something you can explore and understand how it bends and twists in different higher dimensions. So you need to think and I would say extend your critical thinking up to different dimensions. And what are the relations between shapes? Because able to see how shapes relate to each other and how they can be transformed is important. So visualizing how a sphere can be deformed into an ellipsoid requires a good understanding of spatial geometry or spatial reasoning. So this is something which will be required. Also the rotations and folds, because the geometry that you will see now, it won't be the same. It will rotate. So geometric rotation, transformation of coordinates, it will fold. So those things will be required. It would require a kind of a logical reasoning and the connecting concept. That means differential geometry, all those logical reasonings, how it can be connected to other areas of mathematics. For example, real analysis, maybe some part into perturbation theory, etc. So that will also take care of that. So what kind of geometry? These are the kinds of geometry. Those which has got rotation, folds, higher dimensions, relationship between shapes, etc. Now you might have a question, well, all those things are fine, but how do we inculcate, how do we learn those things? It is not an easy task to do. So the first thing that you can do is that you can practice with puzzles, because Rubik cubes or tanograms can help you to improve to visualize and manipulate shapes in 3 dimension. Logical games, yes, you can play Sudoku or chess and can hone on your analytical and thinking and problem solving skills. Modeling software, yes, experimenting with 3-dimension modeling tools can give you a better feel for how shapes behave. So what I can say that by actively developing these skills, you will be all prepared to tackle the challenges and enjoy the best beauty of differential geometry. So this is the kind of geometry that you need to know, and obviously the question would be, what is the best book to develop a geometrical understanding? Now to be very honest, there cannot be any one book, there cannot be a single book, but this transition from Euclidean understanding of shapes to a very abstract, weird, non-Euclidean bending and twisting world, this can be done through one book, and I'm going to recommend that book. But before that, let us see that what the different editions, so that when you are purchasing you are not confused. So Euclidean and non-Euclidean geometries by Marvin J. Greenberg. This is the first, second, third and the fourth edition. Possibly I think on Amazon this is the fourth or maybe the fifth edition. And remember, this contains a total of 665 pages. So again, a thick book is better because it will give you a very detailed understanding. Now why I'm suggesting this book and not going directly into manifold is that this book will give you a transition phase from the understanding of Euclidean to non-Euclidean. So the lines, shapes, angles, triangles, these will be covered, and then it will take you into the non-Euclidean part. So this is Professor Marvin J. Greenberg, and he actually got his doctorate from Princeton University under the famous great mathematician Serge Lang. And Serge Lang also had great books on linear algebra. Now before I go into the content of the book, as I tell that before picking up a book there are certain things which are very important for you to learn, and these are what are called the reviews. And all the reviews, believe me, on Amazon etc. are super, world class, great, remarkable, 4 stars exactly as it described. So this gives you, and most importantly it will also give you this important point. So who can read this book? Prospective high school and college geometry teachers are represented with a rigorous treatment of the foundations of Euclidean geometry and an introduction to hyperbolic geometry. So first the foundation is made clear, and then we go to the new geometry. Also general education and liberal arts students are introduced to this part. That means those who are not from the typically mathematical part, so they can also read this book. The next important part is that what Professor Greenberg tells is that if students do not do a good number of exercise, they will have difficulty following subsequent chapters. That means it is a kind of a nice, I would say, honey trap, that you have to do the exercises and then only you can understand the subsequent chapters. If you skip, you are not going to learn that. And it is good by the author, Professor Greenberg, had done that so that he is making you bound to do those exercises so that you can understand and the understanding becomes better. A quick understanding of I would say the content. You see, again, it starts entirely with Euclid's geometry, and it deals with the Pythagoreans, the Euclid of Alexandria, the power of diagrams. It gives you an account of the history also, and it will teach you the geometry also. It starts with Euclid's geometry, for example, first for parallel postulates, attempts to prove the postulate, and the diagrams also are quite nice, clear, descriptive. Then it goes into chapter 2 into logic and incidence geometry, where the theorems and proofs and those ifs and the conditional statements, how this came from, these are all being dealt in an excellent manner. It also follows with Hilbert's axioms, the axiom of betweenness, the betweenness axiom 1, 2, 3 and so. Then it comes back to neutral geometry with parallel axiom, with Chauchery and Lambert's quadrilaterals, angle sum of a triangle, and nice. So till chapter 4 and 5 it is all speaking about Euclidean geometry. Chapter 6 takes on to the discovery of the non-Euclidean geometry, that is Gauss, Lobachevsky, the defect, the similar triangles. This is the picture of Riemann, Gauss, Lobachevsky, and the strange new universe, that is the non-Euclidean universe. What I was telling, that geometric transformation, because once you move from one coordinate to another, how the geometric, I would say, transformation are taking place, motions and similarities, Felix Klein's Langen program, and everything, half turns, parallel displacement, etc. So you see that once you get to know about the transition, it becomes easy for you to understand. Further results in real hyperbolic geometry. This will actually start with Bolyai's construction of the hyperbolic circumscribes, cyclic on a triangle, hyperbolic trigonometry, etc. So this part of the book will give you a transition as well as an understanding from the usual geometry, from the mental setup you have to the new mental setup which you're taking up. The next book would be more on the historical part, but I found it great, and it is called Worlds Out of Nothing by Professor Jeremy Gray. Now this, I would say this title, Worlds Out of Nothing, I have discussed it in one of my live also. This is coming from the famous quotation of Janus Bolyai, the son of Farkas Bolyai, another great mathematician, who at the age of 13 discovered hyperbolic geometry, and at the age of 13 he wrote to his father that out of nothing I have created a new world. His father was convinced that his son is not speaking sense, and he sent that letter to Carl Gauss, who did not reveal that, and that shocked Janus Bolyai, never could recover, and he left mathematics. So this line, worlds out of nothing, reminds me of the story of Janus Bolyai, that father, I have created a world out of nothing at the age of 13. Tremendous. So this is Professor Jeremy Gray, who is mostly known for writing history of mathematics, and he has got a lot of great books. I have read few of them. For example, The Life of Henri Poincaré, The History of Real and Complex Analysis, The Hidden Harmony, that is the Geometric Fantasies, and Change of Variation. This is a great fascinating book about the history of differential equations, how it developed, etc. So these books will give you a basic understanding of what is the geometry, the mental setup, the mental preparation, and understanding the history, and moving from the traditional Euclidean to the non-Euclidean geometry. Now, before I go ahead in the next part of the video, there is one thing which is very important and most of the students ignore, is that there are certain critical factors in the sense you should be quite aware, and you should take proper steps in learning some of the critical factors in learning differential geometry, which I would like to show you quickly coming up into the next part of the video. Now, the first part that we have already discussed is that it relies heavily on the concept and tools of differential calculus. So what I would say, it follows from the next step that recheck your concepts of calculus, because if there is a gap in terms of understanding of your differential calculus, any concept, any idea, it is not going to help you. So please go back and check on all the rules, all the ideas, all the mathematics of differential calculus. The second thing would be this one, which heavily relies on Euclidean geometry. I don't think you will be facing any problem because you're quite good in terms of Euclidean geometry. The last part will be this one, which I will speak in the next part. And this is the most difficult, I won't say difficult, challenging part, which comes as a bottleneck for learning differential geometry, is that it relies on a proof-based mathematical system. Now, when I talk about that these are the critical factors, you might have again a question in your mind, which is this, that why you should learn differential geometry. We understand you're learning for the sake of your examination or getting a good score, but there are certain other reasons which are beyond mathematics, which is the reason which are could be cited, and what are the reasons you should learn differential geometry. First, you will see that learning calculus will become much better. Because as you will go more deep into understanding differential equations, you will see that learning the calculus becomes better. And it often happens to us that when we are learning one subject which depends on another subject, the earlier subject, the methods becomes clear. Also, it is a very fundamental understanding of concepts, and it will enhance your problem solving power. I mean to say, you will see that those things which will come as proofs, this will help your problem solving power, and it will deepen your understanding of space, because space, as you understand, plane space, Euclidean space or rectangles, these are not so. You can connect those concepts with physics, engineering, robotics, etc. Obviously, without mention, general theory of relativity is one of the areas which will be explored more and more in differential geometry. Robotics, yes, you can learn a lot. Computer graphics, AI and data science, genetic engineering, and many other factors. The idea behind telling you about this part of the video is that you will see that learning differential geometry is not only for mathematics. I remember about 2 years back, one subscriber giving me a call from London. I forgot his name, and he told me that I have seen your differential geometry video, and he is an architect. He makes building, he makes interior shapes of different beautiful offices and malls, and there he is using differential geometry. So it has nothing to do with physics engineering. He is an architect and he is designing nice buildings, rooms, etc. And he told me that, Shaunak, I found your differential geometry videos great. So this is a wide expanse, a variety of domains which embraces the entire power of differential geometry. Now, in terms of learning differential geometry, another concept which often comes up, and it creates a confusion, or I won't say confusion, it actually tells us that, okay, tell me that is it necessary to learn this? And this is called differential geometry and topology. There is overlapping, there are certain questions in your mind which I will clear up. Differential geometry and topology, let us understand what I would say the relation or what would be the differences in the next part of the video. Understand one thing, the differential geometry actually focuses on smooth manifolds. Now, what is smooth manifold? I will later explain you, but this is something very smooth. And this uses calculus. Topology, remembered, it actually speaks of deformation. So you're taking a kind of a shape, you're deforming it, stretching it, twisting it, bending it, and but the shape remains the same. And it heavily depends on what is called the set theory. So the key concepts are what? In differential geometry, it is connection, geodesics, etc. But in key concepts of topology are holes, donuts, connectedness, homotopy, all those things. You can just think this to be a kind of a balloon which has got different types of shapes, angles, and twisting. This topology is typically referred to as a donut and a coffee mug. So for a topologist, both a donut and a coffee mug are the same. Why? I will tell you later. Or you can look into my playlist on topology, you will get the answer. So differential geometry, as I told you, it depends on the bending of curves, etc. And you can imagine a donut turning into coffee mug turning into a donut. So it is continuously deforming into one another without breaking anything. So this is, I would say, the relation or the difference. Now, the important part is that both the subjects, I mean to say differential geometry and topology, both of them deals with explaining the properties and of these shapes, how they behave, etc. As a result, differential geometry and topology are closely related. So many concepts in differential geometry, such as manifolds, are also taught in topology. So there are overlapping concepts, there are overlapping areas, because both these disciplines try to explain the shape and sizes of objects. So differential geometry often studies smooth manifolds. It uses calculus for derivatives, integrals, etc. And there is a subfield which is called differential topology, which studies the interplay between the smooth structure and topological properties. But topology uses concepts like open sets, continuous functions, and homeomorphism. Now, why I'm showing all those things, I will explain to you now. Now, this part, the differential geometry, is something which as I told you, is something very local in nature. Now, as I talk of local, it reminds me of that idea that also gravity is a manifestation of a space-time curvature on a local area. So, because differential geometry is defining or redescribing gravity or general relativity, that also takes into account a local area. General relativity or equivalence principle, if you go to the concept, it is got local. Everything is local, not global. So, all this relate to what infinitesimal changes around a specific point, just like this. It is local. But as you can see, topology is global. And the reason is simple. That deals with properties of space that remains the same under continuous deformation. That means the properties, I would say, depend on the overall structure of the space, not on the intricate details of a single point. It's a huge difference between differential geometry and topology. Differential geometry would be for a small neighborhood around a small area which defines those changes. But here this is a continuous change. That means on the overall structure of the space is dependent, not on a very intricate details of a single point. And that is why you will see it is easy to learn and topology is much more challenging. So the question which arises in your mind is that while learning differential geometry, can you skip topology? The answer is a big yes. Because at the initial level, you don't need topology. If you know certain foundational concepts, fine. If you don't know, that is also fine. Ignoring topology, however, would limit your understanding, but it won't stop you from making a very good understanding of differential geometry. So be prepared that yes, topology can be ignored and you don't need to learn topology at the basic level. Now, when I talk of differential geometry and topology, you are also will get confused while checking out books. That means when you're selecting a particular book of differential geometry, you need to be aware, assuming that you don't know topology, some of the factors which I will now explain in the next part of the video. So when you are selecting a book, point number one is that some book assumes that you know topology. So please be aware. Some authors at the beginning they state, some of them do not. So please be aware about the second point. Please read and check out before you start reading the book. And if you do or do not know topology, select the book accordingly. So the selection of the book has to be done accordingly. Without that, don't select the book. Now let me give you an example. For example, these two books, I will show you what these books are. It clearly tells, I have underlined that in red. We shall prove these assertions as proper discussions of simple connectedness would take us too far into the realm of topology. Since we are not assuming that readers of these books have extensive familiarity with topological ideas, we will not be able to give complete proofs, etc. So these books are assuming that you do not know topology. I will show you later also when I will discuss about these books. Selecting those books are important, and these are few of the points that if you select a book and after reading certain part you really don't understand, and then you understand that it is telling about topology, a subject that you don't know, so beforehand it is better to be aware about that. So you need to check on that. Now we come to the central part of our video, is that what are the mathematical prerequisites of differential geometry? What mathematics you need to know, coming on to the next part of the video. Not much, for a very good news for that. First of all is calculus, second would be linear algebra, third would be real analysis, and fourth would be Euclidean geometry. I know that you would get through calculus as well as linear algebra as well as Euclidean geometry, but thing which you will be stuck and which is going to take some time is real analysis. And that leads to the question that why do we need proofs? And how we are going to learn the proofs, because a lot of differential geometry theorems, etc., depends on a proof-based mathematics, and you really have to prove that in order to learn differential geometry. So first of all, you need to understand is this, that one of the central concepts of differential geometry is that proofs establish how curvature, etc., is defined. Now, differential geometry is full of important theorems. For example, Gauss's theorema egregium, which is a beautiful, you all know what is theorema egregium, one of the most important and beautiful theorems of Carl Gauss. And it also depends upon what is called the proof. The proof actually unlocks this powerful connection. Differential geometry studies how geometric objects like curves, surfaces interact. So you also need to have a learn to proof. And proof techniques can be generalized and applied to new situations, and this makes the mathematicians and researcher make groundbreaking and new discoveries. So all the theorems, any book you pick up in differential geometry would depend upon a proof. And I have seen that students, learners, they can get through calculus, linear algebra, geometry, but what they're stuck about is a proof. And this leads to the question and an answer to the next part of the video, how to learn proofs. And these are some of the book recommendations for learning proofs. The first thing we need to understand that proofs are difficult, proofs will take time, proofs require a different kind of a thinking, and all you need to do is practice, practice, and practice. The books that I would show you now, again, you don't need to pick up all those books, but any one book which suits with your requirement. The first is Joel David Hampkins' Proof and the Art of Mathematics. And I like this because it shows mathematics is an art, because one proof can be done through many. So you see a beautiful girl who is sitting with a basket of vegetables. This thing you can draw in many ways. So that is what is an art. So proof is also, it is an art, and that is why it is called the art of mathematics. I would say this is a very, very basic, a very simple introduction, nothing much of mathematical maturity, etc. required. So you can see multiple proofs, number theory, order theory. At the end, it speaks about real analysis. Around 150, 160 pages book. Good, you can go through to have a basic understanding. The second or a little bit more serious book is this one, Matthias Beck and Ross Goegenhagen's The Art of Proof. And this book again has got an important point, and it tells that now you have reached the stage where the details of what you already know have to be refined. So these books again speak of a very important point, that it is talking of refining your understanding. You need to understand them from a more advanced point of view. We want to show you how this is done. Very important. We will take apart what you thought you know and reassemble it in a manner so clear that you can proceed with confidence to deeper mathematics. And what are the topics? You see, the author is given algebra, analysis, combinatorics, geometry, number theory, statistics, topology, etc. So what you have learned is being refined. Number one, you will be shown how this is done. And this will reassemble things in such a great manner that you will be able to do deeper understanding of mathematics. Here are some of the glimpses. It starts with integers, natural numbers, some points of logic. Logic is important, right? Recursions, then it will start with equivalence, real numbers, limits and other congruences, rational numbers. Great. You see 179 pages. Good book. Continuity and uniformity, and this is plain in English language, is simple. You can go through this book. The next book, a little bit unfamiliar one, Introduction to Mathematical Proofs and Transition. It again speaks of transition to advanced mathematics. It will speak about logic, deductive methods, etc. This is a little bit thicker than the earlier one, around 400 pages. So mathematical induction, which is very important. Cardinality of sets, again important. Relations, all those signs, relationships, functions, everything. So if you talk of the priority, I would say this one would be much read first rather than the other book. The next book is by the famous author Daniel Solo. And I don't know whether you know about Professor Daniel. He has done his PhD and is a professor of operations, pursue several streams of research. The first area is complex systems, which are systems made of a number of individual agents that interact in complex ways. So he has developed mathematical models that provide insights on how much interaction among employees and managers is good for performance and the role and the value of leadership. This is his email ID and this is his phone number. I mean to say this is given over his book and the website of his. And he has given, birth to a lot of great, I would say mathematical ideas. So one book is The Keys to Linear Algebra, The Keys to Advanced Mathematics, and Linear Programming, and Introduction to Finite Improvement Algorithms. So if you talk, Daniel Solo is not typically a mathematician, but, great contribution. This book particularly, How to Do and Read Proofs. So if you talk of the book opinion, I would say this one. This book is well written. I mean to say this is, it's simple. Great was for explaining process behind proofs. And I also feel that mathematics should not be an exclusive club. So it would be so for all of you. And you can also go to willy.com for a perfect introduction to mathematical logic. It should seriously become a part of secondary education, as these tools I feel are invaluable. For those already familiar with concepts, it might seem a bit detailed, but it is a fascinating read. So let us look into the content of the book. This is what the book talks about. What is a proof? Quantifiers 1, 2, 3 and 4. The content talks of the construction, contradiction method, the uniqueness methods and all those. And then it finally concludes with the axiomatic systems, generalization. It's a very good book. It contains proofs and it will make you understand all those proofs. So this will give you an understanding, a better idea that when you will encounter the proof part, theorems, etc. in differential geometry, you won't face a problem. Pick up any one of those books. All of them are equally good. Now, when we talk of the learning of the differential geometry, the concept that comes in our mind is that what is the first step? We understood calculus, we understood different geometry, we understood proof-based mathematical system. What is the first step that we will take in understanding differential geometry? The first is curvature. And curvature means that the amount by which it bends or curves. So the curvature of a surface, we can see that is the amount by which it bends or curves in two dimensions. The second thing which comes are manifolds. Manifolds are simple, that if you zoom, for example, this surface, now if I take this red portion and if I zoom it, it will become just as a locally Euclidean. So manifolds have a certain number of dimensions and it is a small enough regions which looks flat. So again, this is a torus. If I put a magnifying glass over it, it will look just like a flat surface. And this is the main idea of manifold. So a small neighborhood around that point can be smoothly transformed into Euclidean space. So again, it is a neighborhood. That means it is local. And that is why we are using the concept of differential geometry. Same manifold will be extended in topology, which we will later you can look up into our topological videos. So in general, what happens when you are selecting a kind of a book, for example, the learning starts first either with curved surfaces or with manifolds. Most of the books you will see that first chapter is either manifold or curved surfaces. However, what we are going to do is that we are going to start with curves and surfaces and we will take up manifold later, and in the next video I'm going to talk about this part. What is the first step you need to do? How to learn curves and surfaces? What are the intricate mathematical details? And importantly, the learning process and the book. So that gives us a complete thorough understanding of how to learn differential geometry. But remember, this is just part 1. So I would like to take Thank you everybody for watching this video. If you have liked this video, please hit on the subscribe button and click on the bell icon to get all the notification from Physics for Students. You can contact me at this email ID, and you can subscribe to my other channel, General Relativity Explained, exclusive to Einstein's General Theory of Relativity. You can follow me on my Facebook, LinkedIn, Instagram and Twitter account. That's all for today's video, part 1, and we will continue, and I will be covering a complete set of videos unearthing all the difficult and intricate complex concepts of differential geometry, along with the books, resources and whatever is required to learn. Thank you very much for watching Physics for Students. I will be soon back, and few important announcements coming up for the podcast part, which will come one by one. We'll see you soon in the next video, but till then, goodbye.